In the early 1900s, a young Albert Einstein revolutionized our understanding of space and time with his groundbreaking theory of special relativity. This theory was not just a minor adjustment to existing ideas, but a complete overhaul of how we perceive the universe. This revolutionary theory emerged from the clash between Newton's well-established laws of motion and Maxwell's equations of electromagnetism, which describe the behavior of electric and magnetic fields. Einstein's insights unveiled a universe far stranger and more complex than we could have ever imagined. Special relativity, as its name suggests, deals with the special case of objects moving at constant velocities, a state known as uniform motion. This was a significant departure from the previously accepted Newtonian mechanics, which could not fully explain the behavior of objects at high speeds. At the heart of this scientific revolution lie two fundamental postulates that would forever alter the landscape of physics and our understanding of the cosmos. First, Einstein declared that the laws of physics are the same for all observers in uniform motion. This principle, known as the principle of relativity, means that no matter how fast you are moving, the fundamental laws governing the universe remain unchanged. This seemingly innocuous statement has profound implications, as it implies that there is no absolute frame of reference in the universe. In other words, there is no single correct perspective from which to measure the properties of objects in motion. Second, Einstein postulated that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This means that whether you are standing still or moving at a significant fraction of the speed of light, you will always measure the speed of light to be the same. This seemingly simple statement, rooted in experimental observations, shattered the Newtonian view of a static absolute time and space. It introduced the concept that time and space are interwoven and relative, depending on the observer's state of motion. The consequences of these postulates are far-reaching, leading to bizarre yet experimentally verified phenomena, such as time dilation and length contraction. Time dilation means that time can slow down for objects moving at high speeds, while length contraction implies that objects can appear shorter in the direction of motion. These effects, negligible at everyday speeds, become increasingly pronounced as objects approach the speed of light, the ultimate speed limit in the cosmos. As we push the boundaries of our understanding and technology, the implications of Einstein's theory continue to inspire and challenge physicists around the world. c, holds a special place in the realm of physics. It is a universal constant that has fascinated scientists for centuries, serving as a bridge between the macroscopic and microscopic worlds. It is not merely the speed at which light travels, but a fundamental constant that governs the very fabric of spacetime. This constant is woven into the equations that describe the universe, influencing everything from the behavior of particles to the expansion of the cosmos. According to Einstein's second postulate of special relativity, the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This groundbreaking idea revolutionized our understanding of space and time, leading to new ways of thinking about the universe. This means that whether you are standing still, running towards a beam of light, or traveling away from it at high speed, the light will always appear to travel at the same speed, approximately 299,792,458 meters per second. This constancy defies our everyday experiences and challenges our intuitive understanding of motion and speed. This counterintuitive concept has been experimentally verified time and again, solidifying its place as a cornerstone of modern physics. From the Michelson-Morley experiment to modern-day particle accelerators, the speed of light remains a steadfast constant, unaltered by the passage of time or the changing conditions of the universe. The constancy of the speed of light has profound implications. It serves as a cosmic speed limit, dictating the maximum speed at which information and matter can travel. This limit shapes the structure of the universe and influences the behavior of everything within it. It implies that time and space are not absolute but rather relative concepts, dependent on the observer's frame of reference. This relativity means that time can stretch or compress, and distances can contract or expand, depending on the relative motion of observers. This realization, a radical departure from classical physics, paved the way to the strange and wonderful phenomena of time dilation and length contraction. These effects, predicted by Einstein's theory, have been confirmed by numerous experiments and observations, from the behavior of particles in accelerators to the precise timing of GPS satellites. The speed of light, therefore, is not just a number, but a fundamental aspect of the universe that shapes our understanding of reality. It connects the smallest particles to the largest structures, linking the quantum world with the cosmic expanse. As we continue to explore the mysteries of the universe, the speed of light remains a guiding constant, illuminating the path of discovery. Section 4. Time dilation. Time is not absolute. One of the most startling consequences of special relativity is the phenomenon of time dilation. This effect, counterintuitive yet experimentally verified, reveals that time is not absolute but rather dependent on the relative motion of observers. Time dilation dictates that time slows down for an object in motion relative to a stationary observer. Imagine two identical clocks, one at rest on Earth and the other on a spaceship traveling at a significant fraction of the speed of light. According to special relativity, the clock on the spaceship will tick slower than the clock on Earth, as observed by the Earthbound observer. From the perspective of the spaceship's crew, however, time would appear to flow normally. This discrepancy arises from the constancy of the speed of light. Since the speed of light is the same for all observers, regardless of their relative motion, something else must give way to accommodate this. That something is time itself. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. Section 5. The Space Traveler and the Earthbound Twin. To illustrate the concept of time dilation, let's imagine a classic thought experiment involving identical twins. One twin, whom we'll call Stella, embarks on a high-speed space voyage while her twin brother named Alex remains on Earth. Stella's spaceship accelerates to a significant fraction of the speed of light and travels to a distant star system before returning to Earth. Upon Stella's return, a remarkable difference becomes apparent. Stella is noticeably younger than Alex. This difference in aging is not due to any biological factors but rather a direct consequence of time dilation. During Stella's high-speed journey, time slowed down for her relative to Alex, who remained in a weaker gravitational field on Earth. From Alex's perspective on Earth, Stella's clocks, including her biological clock, were ticking slower. From Stella's perspective on the spaceship, however, time flowed normally. This apparent paradox highlights the relative nature of time in special relativity. Time is not an absolute, universally ticking clock. but rather a quantity that depends on the observer's frame of reference.